Right, I think we're probably good to go. So, good morning again, everyone. It's great to see so many of you have joined us this morning, and thank you very much for turning up today for what we hope is going to be an informative and insightful webinar for you. So, I'm Niall Dowds. I am the distribution consultant here at Zurich UK, and it is my pleasure this morning to be helping to host our webinar, which is all about, as you can see on your screens, battery energy storage systems and fire safety. Um, I'll do a little bit of housekeeping, if that's all right, just before we kick off, to let everyone know this call is being recorded. So we'll be able to send that around after we've uploaded it to YouTube. So please keep your eyes peeled. If you have any colleagues that weren't able to attend today, they're more than welcome to go ahead and watch that video. So we'll send that link around when it's ready. Um, in terms of the format of today's webinar, we're going to run questions at the end. So if you have any questions you brought along with you today, or if anything springs to mind as Chris is talking, please feel free to throw it into the Q&A function in the chat, and we'll try and pick through as many of those as possible. I'll move on to a very brief introduction of Chris shortly, but Chris Bottomley, he's our specialist risk engineer over at Zurich Resilience Solutions, and I'll let him do a full intro of himself. But in terms of any questions, it's worth bearing in mind that as a risk engineer, if you have any claims or underwriting questions, they might not be we might not be able to answer those on today's call, but we'll certainly take those offline and get back to you as soon as we can. So just checking if there is anything else that I've missed. I don't believe there is. So, Chris, if it's okay, I'll pass over to
Yep.
you.
Okay then, thanks, Niall. Right, good morning, everybody. I'm Chris. I'm a risk engineer with ZRS and have been for a couple of years now. Before that, I spent the best part of a decade commissioning and troubleshooting battery energy storage systems, solar PV parks, the more larger ones that you'll see down the motorways that cropped up over the last decade or so, which are generally directly connected to the grid rather than the smaller domestic rooftop ones, which are popped up a decade or so ago. So yeah, today we're going to talk about modern battery uses, purposes, how they're used, the risks associated with them, and how we can manage those risks. So we'll move into the next slide. Yeah, we're in the 21st century now. We use batteries for almost every single purpose you can think of now. 30, 40 years ago, the only real use for a lithium battery was in digital watches. Everything else was mostly lead acid batteries. So why we started using these? Well, we're using devices like mobile phones. The first mobile phone that came out was more or less a car battery with a phone stuck on top of it. They progressively got a lot smaller, and 20 years ago we had flip phones, which were small enough to put into your shirt pocket. So how did that happen? Well, we started using batteries which were much more energy dense, and that generally has been off the back of lithium-based batteries, nickel metal hydrides, and the likes. Lithium batteries do tend to allow the power to be used better, so they progressively got favored instead of the other types. So what do we use them in? Well, pretty much anything that uses electricity these days, even vacuum cleaners. But the ones day to day we're all using now is phones, laptops, portable power packs, batteries for drills, and even camping generators, which is in that picture there at the bottom right. So I'll start off with the utility scale battery energy storage systems. That was my bread and butter, and maybe the main reason why a lot of us are here. These started cropping up about just under 10 years ago in the UK. Why? We've got quite a weaker grid on this little island than the rest of Europe had. So in Europe, they can rely on countries next to them a lot more for propping their own grid up. We, however, don't have that luxury, and so as we use more power progressively, the national grids had to come up with ideas to make the grid more stable, and that was the primary purpose, to my knowledge, that battery energy storage systems were being introduced 10 or so years ago. How do they support the grid? At peak periods, they release their energy when there's higher demand. So let's say from 3 o'clock in the afternoon until 8 o'clock at night in winter, this is when the highest demands for the grid are on. Where do they get that energy from? Well, it's either from renewable energy sources, or late at night when the electricity is cheaper. So we have various reasons why these sites exist. But yeah, originally it was for grid support, but now it's energy trading. So you can make money buying cheap electricity and selling it when it's in demand more. Excuse me, I'll just get a drink. So what's in a battery energy storage system? Well, first off, it's batteries, large ones. These ones are the size of shipping containers, and there are multiples of them. As a rough guesstimate, each shipping container sized battery container is between 3 and 5 megawatt hours of available storage. This can get quite difficult to convert that energy, which is stored as DC energy or DC current. It has to be converted to AC to get into the grid. There to date hasn't been a battery made that can store AC energy or electricity in the form of AC. So you have to convert it back and forth. If you're importing from the grid, you'll be converting AC electricity into DC and vice versa. So that uses what I would call inverters, but they would be a converter in this case. In addition to that, you need management systems. Connecting to the grid isn't a simple task. If you connect to the grid incorrectly and you're out of phase with the grid, things will explode, unfortunately, and the management systems will, for starters, on the grid monitoring side, make sure that everything is aligned. The monitoring systems also measure the temperatures of the internal temperatures of the batteries and operate the HVAC systems as well. So we need HVAC systems because batteries tend to get warm when they've been worked. All forms of energy conversion release some heat. And the other components are grid transformers, HV switch gear, switch rooms, and the likes, all designed to allow connection to the grid so that you can import and export the energy. There are some problems, unfortunately, with using batteries and transformers and large electrical circuits. There are risks. Things can catch fire. So, for instance, a standard electrical fire from a loose connection or a cable that's deteriorated or has been squashed, a fire can emerge from that situation. Transformers, they can, if not maintained, or they can catch fire as well. They contain thousands of gallons of mineral oils, and the one that we've probably heard a lot of in the newspapers is thermal runaway of batteries. Thermal runaway is when the internals of a battery get hot enough that, well, this is a lithium-ion battery, the internals get hot enough that it starts releasing its own oxygen. So it's not a traditional fire. And they can self-reignite when they still contain that heat inside them to allow that oxygen to be released. Lithium-ion batteries are very good for charging and discharging. As I said before, they're energy dense, but there is a risk that if they do internally get very hot, a thermal runaway event can happen. So common triggers for this is overheating, as I said, damaging. Some lithium-ion batteries are actually in the form of a pouch inside a racked module. So not exactly resilient if things can get dropped on them, or they can get damaged. So what's the impact? Well, start off a fire that can be very difficult and challenging to put out. Explosions can happen, as a buildup of flammable gases could occur inside these battery containers. And then we've got environmental issues, because the chemicals that are released if a fire does occur are not particularly pleasant. We've got hydrocarbons, hydrogen fluoride, hydrogen chloride, all possible chemicals that could be released in the event that one of the containers does actually catch alight. So how do we try and manage these risks? Well, I've heard that our fire engineers use the Swiss cheese methodology very regularly, which is by putting multiple layers of forms of protection in place. I think the idea is that a piece of Swiss cheese, or a slice, there's obviously holes in it, but if you put them on top of each other, eventually you won't be able to see through those holes, because the other slice has covered one of the holes. So we start with prevention. The first line of defense on a battery storage site is the management system. This continuously monitors the internal temperatures of the batteries. It will, in the event that one is overheating, it will ensure that it's isolated to start with, disconnected from the rest of the group, and then it will start managing via fans and HVAC systems on trying to cool down that battery. That battery might then be set aside, not used anymore until the technicians had a look at it and maybe replaced it. Yeah, that's prevention side. Detection. Up in the top of this picture here, we've got smoke and heat detectors. Generally, you can get faults here where one has failed, but it won't trigger the system. You're probably looking at a double knock system in this particular one. And one other detector that could be very useful as well is an off-gas detector. A battery, a lithium-ion battery that is getting very hot, but not quite at thermal runaway levels, temperature levels. About 20 degrees before that, it will start emitting some hydrogen gases or flammable gases. So the off-gas detector will actually spot those gases, hopefully 20 degrees or so before the battery does get violent, and we can isolate the system there, cool it down as quickly as we can, and we've obviously avoided a nasty situation. So off-gas detection is a very useful form of nipping things in the bud there. Evacuation. So if bad things are happening inside a battery container, we don't want those gases building up in there. You'll see a picture on the next slide, I think, where the actual build-up of the gases can be quite dramatic. This is basically a venting system in the roof of the containers. They will open if these gases are spotted by the detection systems, and it will clear it all to prevent explosions and the likes. So the one I like personally, which on utility scale battery storage sites, this is the one that makes the most sense to me, is whilst it's not inevitable that a battery container develops a problem, if it's far away, I wouldn't say far away as in 200 meters, but if it's separated from the next door container, you've limited any problems to one container. So the NFPA came out with a value of 3 meters separation between one container and the next. There can be some small changes to this. For instance, I think it's if there's a 2-hour firewall either between two containers or built into a container, they can be positioned closer to each other. But a general rule of thumb is minimum of 3 meters. Suppression systems. Right, so like I said earlier, there's electrical risks, not so much inside the battery, but auxiliary systems, networking systems for the plant controllers. A fire could develop inside those. So suppression systems such as aerosol generators or can't remember the name of the gas used, but gas suppression systems. These could be used to prevent an electrical fire from spreading in one of those systems, maybe on a busbar chamber, but they wouldn't work very well in the event of a thermal runaway event. And the analogy I would use there is kids' birthday cake candles. If you use the trick ones that reignite themselves, this could happen with a battery pack that's undergoing a thermal runaway event. So a one-shot suppression system might lead you into a false sense of security that you've quenched a fire. You may have quenched the fire, but maybe 5-10 minutes later, maybe even hours later, it may reignite itself. So yeah, it's useful, but not a magical solution to it. Structural resilience again, like I mentioned earlier, fire-rated containers would help prevent the spread of fire. So I'll move on to the next slide. So, okay, we've got a list here. I'm not going to read through every single one of these, but they're the applicable codes and standards that we do look for in the design of a battery energy storage system. NFP 855, I touched on that in on the last slide. UL 9540. This is where manufacturers send their battery packs over to the likes of TUV, DNV, these laboratory test companies to do a destruction test on their batteries and check to see how fire is propagated, whether it stays within one individual cell or moves onto a module and the unit and then the battery container. Manufacturers will actually hand these certificates out once their product has passed these tests. So it's comforting. Laboratory tests maybe can't cover every single eventuality, but it's comforting that at least the majority of possibilities has been tested for. NFPA 68 is regarding venting systems. The NFPA 850 is prevalent in anything to do with power generation. And what's the other one? 2001 is regarding the extinguishing system. So, yeah, a good selection there to rely on. What other uses do we have for batteries that have emerged recently? Obviously, there's a picture of a forklift there. It's a recyclable one. Sorry, recyclable forklift. What am I on about? Rechargeable. But yeah, prior to that, we had lead acid batteries. They had two good purposes. Number one, they were heavy, so they'd stop the forklift from tipping over. But as I've said before, the energy density wasn't so great. So there are lithium ion based or lithium iron phosphate based forklift trucks now emerging. They're yeah, they do exactly the same purpose as the original ones. But what I would say, if you're installing a BESS into warehouses, or the forklift truck isn't exactly a BESS, but it is stored energy within that forklift. So I would say a lot of this would apply. But number one is follow the manufacturer's instructions. Read the manual religiously. It's their product. They've put it together, and it'll show you all the safety safeguards, that you need to put in place in order to operate the device safely. Assess the placement of the recharging station for these devices, maybe even in a separate room. It's where am I going with this? It's yeah, you really don't want all and sundry playing around with these things. I would say you need a trained staff member that knows his responsibilities and can prevent other people from fiddling with things, let's say. Right. What else would you need to do? Maybe update your fire systems that are in the building. You need to monitor these batteries. A lot of these devices will self-monitor, but every now and again, maybe just check the batteries if you're putting them into a charging station. Just if they're feeling very hot, let them cool down before you start recharging them again. Why is that? Hot batteries, as I mentioned before, your thermal runaway temperatures, which is around 200 degrees internally. If you're holding a battery that's hot to the touch, that's its external temperature of around 40, 50, 60 degrees. Internally, it may be a lot hotter. So let them cool down. Don't use damaged batteries. If the casing is cracked, it needs to be set aside. Basically, you shouldn't really use that. As I mentioned before, some of the cells are in a pouch form. If that gets ruptured, yeah, you're leaking electrolyte, which could lead to a fire. As I mentioned before, staff training. Everyone should be aware of these topics, and make sure you recycle them safely. There are government regulations now. We've got the WEEE, WEEE regulations for safe disposal of technology. You can even hand damaged or obsolete kit back to the manufacturer if you know where they are. Yeah, it's the lithium inside the batteries can actually be quite valuable in the future. It will need to be recycled at some point. It's not an infinite resource, lithium. It's something we need to keep an eye on. And finally, inform your insurance provider. You've possibly introduced some new risks if you're using these devices in a warehouse. So better to be safe than sorry, and just inform them, let them know what you've got in there. Right, notable incidents. There have been a few. There have been a few dozen worldwide in the last 10 years. The most notable in the UK was at a battery storage site in Liverpool. This happened in 2020. The site was commissioned in 2019, I believe, so it was not an old site. And the local fire brigade had to attend and be on site for 59 hours. They used 2 million litres of water to not necessarily put out the fire, but to prevent the spread of the fire. This battery container, you should be able to see the bulging of the walls here. A lot of pressure built up inside that container, and obviously distorted the walls there. Nobody was hurt. as I said, 2 million litres of water, which is a lot. I don't know what the environmental damage was there. There may have been some runoff. I just don't know. But that's the UK's worst situation so far. I've just gone on to the next slide. Apologies for that. Early this year, in January, the Moss Landing battery storage fire occurred. Just so you know, this is a picture of an old power station from the 1950s. This isn't a battery container. The battery containers are to the right of the power station building. And this was a 300 megawatt facility that caught alight, and they couldn't put it out. There'd been 6 prior incidents, to my knowledge, at this site where the fire department were called out. Obviously, this one was unput-outable. I believe that they use the older generation of lithium-ion or nickel, manganese, cobalt batteries, which are the ones that are notable for going into thermal runaway, and we've improved on that now, and hopefully this is a one-off. So that's the Moss Landing site. 2019, there was a much smaller incident in Arizona at a McMicken BESS. I'll mention this one because unfortunately 4 firefighters were injured. I think it was due to an explosion. Maybe they opened a door when there was a buildup of gas. But yeah, it can be a bad event if battery containers are on fire. Good news is the new technology that we're using, lithium iron phosphate, is a lot less susceptible to thermal runaway. It releases less oxygen. It doesn't want to go into thermal runaway. It needs to be pushed very hard to even go into that state. So with the lessons learned from some of these incidents and following the guidelines, i.e. the separation, using detectors, etc., these problems should be avoided in the future. Well, what's around the corner? Technological advancement. So we've got lithium iron phosphate, the LiFePO 4, which is my battery of choice at the moment. What's coming out, I think even this year, is vanadium flow batteries. These batteries use vanadium, strangely enough, but it's in a water-based electrolyte. They're much larger batteries, but if you're using water as an electrolyte, it's a lot less likely to catch fire. They don't have the energy density though, but they have a fantastic number of cycles that it can go through, 20,000. So as a rough rule of thumb, if you're doing 1 charge discharge cycle per day, that's about just under 11 years. So and equates to about 4,000 charge cycles. So these batteries could be maybe 50 years old by the time they've actually reached the end of their usable life cycle. That looks quite positive to me. Lithium iron phosphate batteries, about 11 years if it's 1 charge per cycle per day. Solid state batteries are also not a million miles away. I saw on Toyota's website not long ago that they will be releasing a working product, I think in 2028. So, excuse me. So instead of lithium ion batteries or lithium ion phosphate batteries in their cars, they're going to be using solid state. What's good about solid state is they don't use flammable electrolytes, and the charge density is a lot higher. So what might be a 300-mile range car could possibly be a 1,000-mile range car. The other one that's coming around is metal air batteries. I don't know much about those, but they are, to my knowledge, the highest density energy that can be stored, may be applicable to usage like satellites, etc. So let's conclude. It's not all bad news. You may have heard or seen a lot in the media about battery storage fires, etc. They do have some risks. They offer a very good potential for us to transition from fossil-based fuels into renewable age. Not fit and forget. Obviously, they need to be looked after. They need to be monitored 24/7, just to make sure that they're operating safely. And the staff that are operating them should likewise be trained up to be able to look after the batteries suitably and understand the mitigation steps that they may need to implement if a battery does start becoming toasty, let's say. So, thank you very much. And I think I may have finished a little bit quicker than expected, but we'll see what some of the questions are, Niall.
Sure. Thank you very much, Chris, for running that through with us. Very, very efficient, as we said. I have a few questions that have been sent through to me personally. Guys, if there's anything else that crops up, as we said at the beginning, please feel free to add those into the Q&A. But Chris, if I just fire some of these across to you now, just to cover off, if that's okay. So the first question is, what is the best fire suppression system for battery fires?
Best fire suppression system. Right. So, well, the best fire suppression system is not having a fire in the first place. So by making sure your monitoring system is working effectively, making sure that your detection is suitably installed. So you'd want detectors at the top and the ceiling of the containers, possibly even at the bottom as well, to make sure you've got the full coverage. Like I said before, the suppression will not work if it's a one-shot gas bottle, let's say, on a battery pack that's already gone into thermal runaway. It's likely to reignite unless it removes all the heat in that battery. There are some gel type systems that are being released to the market. I was at an exhibition in February. I won't name the brands, but they monitor the batteries, and if triggered, they will release some form of gel into the battery packs that will surround those packs and draw all the heat out of them and make sure that the fire doesn't occur in the first place. It sounds promising. I haven't seen it in action though, so it would be nice just to go maybe another step and speak to these companies and see what actually goes on there. So yeah, that's my answer there.
Okay, brilliant. Another question I have is, how long is the expected burn duration and cooling period for a battery in an electric vehicle?
Electric vehicles, wow. I'm used to much bigger batteries than the ones in electric vehicles. Reading from the media and the likes, it's probably in the region of 24 hours. Sorry, hang on. How long will it burn for? If it is a very violent burn, probably a couple of hours until all of the fuel is consumed. Just a caveat here, I'm more on the electrical side rather than fire management side, so I may use the wrong wordage here, but yeah, it could be smouldering for hours before then, maybe until it ignites, but probably a couple of hours. And if nobody's doing anything, I did have one of the fire brigades come to my site, well, one of the sites that I was looking after, and they mentioned that they had developed a bladder, or effectively what's a kid's paddling pool, but for a car-sized EV. And they would quench the fire entirely by dropping the fire into there. Sounded a little bit far-fetched, and I haven't seen much more about that, but that would be quite a quick way of putting it out. That you'd have to set all that up before you could crane the car into that tank. So
Okay.
hopefully that answers that one without.
Yeah. Thank you very much. And a third question I have, Chris, is there a requirement to have a documented battery safety management plan?
A requirement, I believe there is. I don't know whether it's legal, but your local councils may require this if you're putting in your plan for putting a battery storage system in their patch. A good plan will certainly help with the planning application, hopefully get you through, put them at ease that you've considered every single facet of the site, what can happen, and your steps taken to avoid any risk to anybody else, risk to the environment, etc. So it's certainly advisable. Whether it's a legal requirement, I'm not so sure at the moment. I believe the government are mulling over tightening up some of the guidance that they put into place for battery storage systems, though. So watch this space, I would say. It might not be at this snapshot in time, but quite soon maybe strengthened up a bit.
Sure. Okay. An interesting comment from Leslie in the chat, saying that there was a good program on Channel 5 the other night about how safe are EVs, and they included a good section covering fires and how to tackle them. So that sort of covers, I'm sure will cover some of what we just talked about in the last question.
Yes.
So worth checking that out.
Yeah, no, I mean, EVs is a whole different kettle of fish. Battery storage systems, the grid connected ones that I looked after, they're static to start with. They're not driving at 70 miles an hour down the motorway. And you pretty much know what's going on. You're the guy there and you know whether it's running right or not. Somebody in an EV obviously isn't an expert in batteries and is just concentrating on getting from point A to point B. Yeah, there's a lot more risk in an EV. I'm not saying that it's a catastrophe, but there's a lot more to take into consideration when it's traveling down the road. So.
Absolutely. We have a question from Mick asking, does the technology and/or safety protocols tend to work downwards or upwards in terms of BESS size?
Right. Does that mean that all of the monitoring systems that would be in a utility scale site? Well, all of these, let's say like the battery forklift that I put in the picture there, they have monitoring software inside them. So to actually charge, they will need to convert the higher voltage DC from the charging station into the battery packs. They'll need to monitor and manage the state of charge, etc., etc. So I would say probably at least 80 to 90% of the functionality will be there. However, on a utility scale site, you've also got to think about jumping onto the high voltage grid system as well. Yeah, it's slightly different job that they've got, but a lot of the monitoring points that they'll look at will be the same, such as monitoring state of charge, internal temperature sensors, etc., etc. So, yeah, a lot of overlap, but not a perfect overlap.
Brilliant. Okay, thank you. We've got another question from Joe in the chat, saying, with LFP batteries becoming more and more common in many industries, we are seeing this risk come across our desk more often. You mentioned this battery type is less likely to enter thermal runaway. However, it's still possible. And would you say that the safety procedure for storing and using LFP should be on the same as traditional lithium ion?
Well, it's always better to be safe than sorry. They, as I said before, they're a lot more reluctant to go into thermal runaway. I can't give you an exact figure, whether they're 10 or 50 times less likely. But the way that they've been designed is to release a lot less oxygen, and they can be abused to higher temperatures before they do start releasing any oxygen. It's the chemical process that happens when they get too hot is what causes the thermal runaway, and I would say maybe 90% of those steps that can cause the thermal runaway have been avoided using lithium iron phosphate. So maybe they're not perfect, but they're certainly an improvement, and maybe the perfect batteries around the corner. I like the look of vanadium flow batteries for utility scale storage. 50 years, it sounds like a good one to me.
Brilliant. Thank you, Chris. And this is another EV related question. So let us know if this isn't really one you want to cover. But from Nitin, we have how safe are low budget electric vehicles like e-rickshaw used in the poor roads and many times overloaded?
Well, I mean, I'm not going to say anything bad about any brands. That's not what we're here for. But if you're using a vehicle where it can be damaged, where a battery pack can be damaged easily, potted roads, etc., it might not be the perfect application for that vehicle. You want paved roads, by the sound of it.
That makes sense. We have a question from Peter saying, depending on the varying levels of risk monitoring, predictive analytics, prevention, upfront design, system design, does the insurer, I think that's supposed to say, of fundamentally different insurance deals and prices, i.e., is the insurance industry parameterizing their insurance offerings based on the reality on the ground?
I'm struggling to put into thought on that one. Is that one we can come back to later, do you think?
Yeah, that's fine. Peter, we'll
Yeah.
take that one away, if that's okay, and we'll pick it up offline and get back to you. Hopefully be able to answer that one for you. We have something from Sarah here saying, why aren't vanadium batteries used in EVs?
It's the energy density. So vanadium flow, they're what is it, about 4 times less energy dense. The only reason lithium was used in the first place is because it's able to pack a lot of energy into a small watch battery, the first application I'm aware of. So you bought a digital Casio in the early 80s and it would run for a couple of years at least before you needed to change the battery, and that was one of those little button batteries. As demand increased, the uses of lithium and also nickel, been talking too much now, nickel metal hydrides, etc., NiCads, they've all been used as well. Lithium does seem to have pushed them aside now, and I think it's all down to energy density, just the ease of use and fast charging as well.
Sure. That makes a lot of sense. We have a question from Gareth here saying, what is the latest advice about spacing between batteries? Gareth has a client that constructs large BESS sites, and they're always pushing for closer spacing, sometimes less than a meter, for commercial reasons, against insurers' appetite, which leads to much back and forth.
Right. Yes, I can understand that. The NFPA obviously have put their drawn a line in the sand there, 3 meters. If I remember correctly, that 3 meters is for a potential fire with wind at 2 meters per second, and pretty much most days in the UK we've got winds more than 2 meters per second, especially as we head into autumn, etc. It sounds like I say, a good line in the sand to start with. There are some caveats in the NFPA guidance. So, for instance, if the battery container has a fire-rated skin, let's say on the back of the container, away from the doors, maybe they can be positioned back to back suitably, or end to end. But one of the big things as well is these containers have to have doors so that the batteries can be maintained. Somebody's got to go there, open a door, have a look inside, maybe change some racks, change some battery modules over, verify that everything's tickety-boo inside. So you're going to need at least 2 meters just to be able to actually physically look after those battery containers. So that extra meter for peace of mind isn't going to, I don't think it's going to create that much of a problem. Maybe if you add that up, it might be an extra 10 meters to the width of a battery storage site. A lot of battery storage sites are pretty much tagged onto the side of a substation, and many substations are out of town. For that extra 10 meters of space, it might not be a deal breaker. But I can understand that you want to cram things in, but maybe it's advisable not to. So case by case. That's probably
Cool. Thank you very much, Chris. We have another question from Sarah saying fires in electric vehicles get a lot of press attention, yet widely used despite the risk. How do these fire hazards compare to traditional vehicles?
Right. Traditional vehicles, obviously the fuel for the fire is the fuel that the engine's running on. Your tank's normally in the back, and your engine where the risks are in the front. Firefighters obviously have many decades of putting out traditional vehicles, ICE vehicles as they call them, and once put out, it will stay out. Whereas lithium-ion batteries, there are some EVs which have got lithium-ion. EVs, it's a trickier job for the firefighters, I believe, because there is always that risk of reignition. So hopefully that answers that question.
Yeah, thank you very much. Just having another look through. So there's a few questions about us sharing the recording, and we can also share the transcript afterwards. So if anyone's not been able to see part of the recording for any reason, that's absolutely fine. The slides, I'm not sure what we're planning on doing there. Sarah and Chris, if you guys are happy to share, that's fine. If not, like I say, we'll have the transcript and the recording, so you'll be able to see the slides through that at the very least. So hopefully that answers that question. I'm not sure if I can see any more questions that have come through. I think something just come through here from Nitin.